In section 10.3, we're going to talk about the basic theory of homogeneous linear systems. And we're going to be focusing on homogeneous linear systems through section 10.6. In this section, we're going to consider homogeneous linear systems of the form y prime equals a of t y, in which a equals a of t is a continuous n by n matrix function on an interval a to b. The theory of homogeneous linear systems has much in common with the theory of linear homogeneous scalar equations. So we're going to find a lot of commonality. So if y1, y2, all the way down to yn are vector functions defined on the interval ab, and c1, c2 through cn are constants, then y is equal to c1, y1 plus c2, y2 plus all the way out to cn, yn, and is a linear combination of y1, y2 all the way out to yn. We say that the set y1, y2 out to yn is a fundamental set of solutions to the linear system y prime equals a of ty on AB if every solution can be written as a linear combination of y1, y2 all the way out to yn. If this holds true, y equals c1, y1 plus c2, y2 plus all the way out to cn, yn is the general solution of the system y prime equals a of ty on the interval a to b. We have theorem 10.3.1, which says suppose the n by n matrix A equals a of t is continuous on the interval AB, then the set of solutions y1 through yn of n solutions of y prime equals a of ty on the interval AB is a fundamental set if and only if it's linearly independent on AB. Let's look at an example. In example problem 1, we're going to be showing that the vector functions y1, y2, and y3 are linearly independent on the interval a to b. So that means we need to suppose c1, y1 plus c2, y2 plus c3, y3 is equal to 0 on a less than t less than b, right? So we need to show that the only solution here is that C1 equals C2 equals C3 equals 0. So if we were to rewrite this as a matrix, we would then have e to the t, 0, e to the negative t, 0, e to the 3t, 1, and e to the 2t, e to the 3t, and 0. And this will be multiplied by a column vector of our coefficients, and it has to equal 0. So if we expand this system or this matrix here and we look at the determinant, we would find that our determinant of e to the t, 0, e to the negative t, 0, e to the 3t, 1, e to the 2t, e to the 3t, 0 is then e to the t times the determinant e to the 3t, e to the 3t, 1, 0, minus 0 times the determinant 0, let's see here, e to the negative t, e to the 3t, 0, and plus e to the 2t times the determinant 0, e to the 3t, e to the negative t, 1, which would give us e to the t times 0 minus e to the 3t minus 0 plus e to the 2t times 0 minus e to the 2t. So we end up with a negative e to the 4t minus an e to the 4t. So we end up with a negative 2 e to the 4t. Well, this is never going to equal 0 for all t. So that means the only way, the only solution here requires C1 to equal C2 to equal C3, which would all have to be 0. And this means then that our system of solutions, C1y1 plus C2y2 plus C3y3, is linearly independent. So we can write that in. Therefore, y1, the set y1, y2, and y3 are linearly independent. We have a couple of more theorems from this section. Theorem 10.3.2, which is Abel's formula, says that suppose the n by n matrix A, which is a function of time, is continuous on the interval AB. Then let y1 through yn be solutions of the system y prime equals A of ty on that same interval AB, and let t naught be in the interval AB. Then the Wronskian of the set of y1 through yn solutions is given by W of t, which is the Wronskian of t naught times e to the integral of t naught to t of a11 of s plus a22 of s plus all the way out to ann of s ds, where t is in the interval ab. Therefore, either the Wronskian has no zeros on our interval, or our Wronskian is identically equal to 0 on our given interval. So it's either none or all. No zeros or always 0. And theorem 10.3.3 says, suppose the n by n matrix A, which is a function of time, is continuous on the interval AB, and let y1 through yn be solutions of the system y prime equals A of ty on the interval AB. Then the following statements are equivalent, meaning they are either all true or all false. A says the general solution of y prime equals A of ty on AB is y equals C1y1 plus C2y2 all the way out to Cn where C1 through Cn are the arbitrary constants. The set y1 to yn is a fundamental set of solutions of the system on the given interval. The set y1 to yn is linearly independent on the interval. These should all sound like things that we looked at when we were looking at single sets of solutions. Right? When we were looking at a single ODE, we were finding that our set of solutions was linearly independent and therefore formed a fundamental set of solutions. It's the same idea. We're just now taking and applying that into the system. D says the Wronskian of our set of solutions y1 to yn is non-zero at some point, and the Wronskian of the set y1 through yn of solutions is non-zero at all points on our interval. So let's see how we would apply these theorems. So let's take a look at example 2. On the file I uploaded for you, I put the entire statement of the problem on one slide, but I've separated it out into different slides for each part of this problem for the ease of making the video. Okay, it's the same problem, just spread out a little bit more. So we have the vector functions y1 and y2 that are solutions to the constant coefficient system y prime equals -4, -3, 6, 5, y on -infinity to infinity. We want to show that the vector functions are linearly independent on every interval a to b. So what that means is if we were to take the Wronskian, right, the W of t here, Wronskian, would be, in our first column, we would have y1, which is -e to the 2t, and 2e to the 2t. And in our second column, we'd have y2, which is negative e to the negative t, and e to the negative t. And so if they're linearly independent, then we should find out that our Wronskian here is non-zero for all values. Because we were told, it says to verify, but we were told that they should be solutions from negative infinity to infinity. So let's see if that's in fact the case. Well, then we would have negative e to the 2t times e to the negative t minus 2e to the 2t times negative e to the negative t, or negative e to the t plus 2e to the t, which gives us 1 e to the t, which is never 0 for all real t. So therefore, in fact, y1 and y2 are linearly independent. If we want to verify Abel's formula for the Wronskian, what that means then is we've got W of t equaling W of t naught times e to the integral of t naught to t of, and if you look back at what Abel's formula tells us, it says that inside we're going to be adding up all of the functions that are on the diagonals. a11 plus a22 plus a33 all the way out to ann. So here, that would just be negative 4 plus 5 ds. So what that really is the Wronskian of t naught times e to the integral from t naught to t of just ds. Or in this case, we would end up finding out that we have the Wronskian of t naught, which would be negative e to the 2t naught, 2e to the 2t naught, negative e to the negative t naught, e to the negative t naught, times, well, e to our integral of s that goes from t naught to t just gives us e to the t minus t naught. Well, we already know what the Wronskian of the inside looks like because we just did it. And in this case, instead of just having e to the t, we have e to the t naught. And then we multiply it by e to the t minus t naught. And when we add up the exponents, t naught plus t minus t naught, we end up with e to the t, which is exactly what we got in part A. So this is consistent with part A. Oops, with part A. So we've confirmed that Abel's formula for the Wronskian works in this case. For part C, we were asked to find the general solution. Well, since we know, right, since the Wronskian is not equal to 0, we know then that y1 and y2 form a fundamental set of solutions. Right? Sound familiar? So we know then that we would have y equals c1y1 plus c2y2, or y would equal c1, and let's see here, y1 we'd have negative 1, 2 e to the 2t plus c2, we'd have negative 1, 1 e to the negative t, and there's our general solution. Underline that and highlight it for you. There you go. So part D says, okay, now that we know what our fundamental set of solutions look like, now solve the initial value problem where we have y of 0 equaling 4, negative 5. So we know, again, from the previous problem that y is equal to c1, negative 1, 2, e to the 2t, plus c2, negative 1, 1, e to the negative t. What we also know then now is we can plug in this initial condition. So we know that 4, negative 5 is going to equal c1 times negative 1, 2, and well, t is 0, so that's just times 1, plus c2 times negative 1, 1. Or in this case, what we end up with then is negative 1, negative 1, 2, 1 times c1, c2 equals 4, negative 5. And I am going to bring it up here where we have a little bit more space. I'm going to rewrite it as an augmented matrix. So we have negative 1, and then our solutions are is 4. And then we have 2, 1, and negative 5. So first transformation, let's do 2 times row 1 plus row 2 to get a 0 in that first entry on the second row. And then we'll take negative 1 times row 1 is our new row 1. So we'll end up with 1, 1, and negative 4 here. But 2 times negative 1 is negative 2, sorry, plus 2 is 0. 2 times negative 1 is negative 2, plus 1 is negative 1. 2 times 4 is 8, plus negative 5 gives me 3. And then I'll say, let's do negative 1 times row 2 is our new row 2. To make our final step here, we end up with 1, 1, negative 4, 0, 1, negative 3. So we find out then that C2 equals negative 3 and C1 minus 3 equals negative 4. So C1 equals negative 1. So our solution here to the initial value problem then would be y equals negative 1, 2, e to the 2t. Let's see here, C2 was negative 3, so minus 3, and then negative 1, 1, e to the negative t. So we could leave it that way, or if we wanted to move the negative 1 in, we could make it 1, negative 2, e to the 2t, minus 3 times negative 1, 1, e to the negative t, or we could even, there are a lot of different versions of this, right? So we know this is a solution. This is one form of the solution, I should say. So we know we're good here. But if you don't like the negative in the front, you could always say, okay, I'm going to bring some of those negatives in and say, okay, then this is just 1, negative 2, e to the 2t. And then minus 3, negative 1, 1, e to the negative t. That's also a solution. These are all just different forms of the same solution. Well, let's say you really don't like negatives and now you want to get rid of the negative 3. Okay, so now let's go one more step. Y is, let's see here, 1, negative 2, e to the 2t, plus 3 times, you could do 1, negative 1, e to the negative t. And again, I could do another one where I pull the 3 into the column vector for e to the negative t, but that's just even more, even a little bit more extra. So all of those are equivalent solutions. It's all a matter of whether you're leaving the negative on the outside, either for the first, for y1 or for y2. I would take all three versions of this solution. So let's look at what we have for homework. In this section, I gave you problem 7, part A and B, and problem 9.